Hello, everyone. On behalf of the Enkidu training team, I would like to extend a warm welcome to each of you. We are delighted to have you with us today for our webinar, Innovative Water Flooding Strategies for Maximizing Oil Recovery. My name is Mohammed, and I will be your host for this session. The webinar will be presented by our speaker, Mr. Mohammed Al-Jawhar. Mr. Mohammed Al-Jawhar is a senior petroleum engineer with extensive expertise in petroleum engineering, production management, and strategic planning. He is highly regarded for his ability to streamline operations, develop innovative solutions, and identify opportunities for sustainable growth. With a comprehensive understanding of engineering and production protocols, procedures, and industry best practices, Mr. Johar is recognized for his strong communication skills and his ability to build and maintain effective professional relationships with both team members and senior leadership. Before we begin, please take note of a few important points. If you have any questions during the presentation, feel free to type them into the Q&A box. We will answer them at the end of the webinar. Please note that this session is being recorded. Throughout the presentation, we will share relevant links in the chat box, allowing you to connect with Enkidu training on Udemy, LinkedIn, YouTube, Facebook, WhatsApp. And a link to the attendees registration form will be shared at the end of the session. Certificates will be awarded through the Enkidu page on the Udemy website. Now, please join me in extending a warm welcome to Mr. Mohammed Al Jawhar. Mr. Mohammed, we invite you to introduce yourself. The floor is yours.
Thank you, Doctor, again in this free webinar hosted by Enkidu Training. Thank you for the attendees for attending this free webinar. Um, I think can you give me the permission to share the screen, Doctor?
Yes, Mr. Mohammed?
Um, it's not sharing. I don't know. Is it visible to you, the screen?
No, no. Please send me a request in order to um, re-show the document because I shared it already.
Um, It's not working. Just a minute. I think now it's working. It's working now, right?
Yes, that's good.
Great. So yeah, thank you, Doctor, and thanks for Enkidu training, and thanks for the attendees for this free webinar. It will explore some details about water flooding strategies. Hopefully, it will be interested and helpful for you to understand some aspects in water flooding strategies, the innovation in this matter. So we already know something about water flooding. So water flooding, what is it? When we use it? So we will explore in some details in this matter today in this webinar. So the agenda will cover understand what are flooding fundamentals. We just get to go through some simple details about water flooding, water flood design process, innovative water flooding techniques, and challenges in water flooding, technical and economics insights application. So let's start with first topic in our agenda today, which is understand water flooding fundamentals. So, water flooding. So, what is water flooding? We know water flooding, one of the things we use in our uh, field life when we have to support the reservoir pressure, because when you start producing from your reservoir, you will face some challenges regarding depletion of the pressure. So how you can support this pressure? So one of the things we use is water flooding. So it's essential for sustaining production in all reservoirs, because otherwise declining in pressure, we are losing your support for oil production or gas production, and then you will lose the ability of reservoir to produce more oil. So one of the things you are want to use is water flooding. Why? We will know later why we're using this technique to enhance our recovery uh, from the reservoir. So we all know that the field life start from the source rock to the surface, and then to the pipelines to the production tanks, storage tanks, I mean, and then to export. So from the first point, I mean the source rock, where you have pressure and temperature and migrate to traps, there is a long way from that point to the end point. So hydrocarbon formation, we mean when we have start the this trip, this journey from producing oil, and then you have the primary migration, secondary migration, and you have water flooding. So applying water injection to enhance recovery, because somehow we lose from this point to this point some pressure uh, after producing from the field for the first time. So the primary migration, when we have the source rock, and the secondary migration when we have inside our reservoir. So after oil traps in some places, so we extract oil from that places, and then we have using this technique to enhance production. So this is one of the enhanced oil recovery in oil field. So what is the water flooding? What is happening in the field life? We have exploration, of course, when we want when we decide where to produce oil. So we have our exploration phase and discovery and delineation, and then we developed our field. Then we start production. So this from this point to this point, a lot of things happened. One of these things, which is water flooding. So, so this diagram explains the full life cycle of any oil field. Apart from the type of the oil field, is it gas, is it oil, or is it both? So it's going from exploration to abundant. So let's move through our presentation. So water flooding overview. So it's sweeping the oil out with water. Water injected into oil zone. Of course, we know we have to inject some water inside our reservoir. So this means display oil and push it to the producing wells. We know for sure we have reservoir and we have both injector and producers. So we have oil here, and we have water here. So we need to inject water to push some oil to that point and then extract it from the other place. So it's a very simple illustration to understand where we have to push some oil from this point, let's say the A point to the B point. It's a very simple illustration to understand which layer we have to push the oil through from one point to other point. So I understand this and going from this point to understand what is water flooding principle is. Okay, so let's move on. So displace the oil and push it to the producing wells. Maintain reservoir pressure. Of course, we know when we start production, so the oil will rise and then reach what we call it's a plateau rate when the production is stable, and then we will see in some point declining in production. Why? Because we already have a pressure, and that pressure will declining, and this pressure support to the oil production when it's declined. So we need in this point we need to think about what we can do to our reservoir to enhance the production. Otherwise, we will lose production significantly from that oil field, because we know there is no pressure for that there is no support for that reservoir pressure. So what we can do, it's water flooding, one of the techniques we use to maintain that reservoir pressure. Water is an effective displacing fluid because it's simple and cost effective, and it's very simple to use. So what is the economics of water injection? Let's see what is the economics of water injection. It's cost. So water supply wells, water treatment facilities, pump station, flow injection lines, water injection wells. It's considered the most attractive oil recovery method because it's very simple. It's cost effective. Having said that, what is the limitation for that part? Because it's a significant amount of oil is left unrecovered. So because why there's a lot of things happening when we inject water through our reservoir. So we do it when using water flooding techniques. Some part of oil is still left. It's depend on the oil. I mean the field properties, rock properties, reservoir properties. So there's some amount of oil will left. So the reservoir studies will understand why we have like this limitation in using water flooding. So every technique has its limitation, but for instance for water flooding, it's because it's the advantage it's more efficient, the displacing fluid than gas, and readily available at low cost. So it's because it's low cost. So most of the companies looking at the cost because they have a budget. So they need to understand how they can manage that budget. So one of the techniques, cheaply techniques, let's say, that's water floodings. That's why most of the companies do using water flooding, and then they think about if that will enhance the recovery of their field or not. What is the outcome of it? So after considering all the costs for this technique, so it's low cost. What is the disadvantages of that technique? It reacts with reservoir rock. Of course, every technique when used to enhance oil recovery, there is some reaction with the reservoir rocks. It depends on the reservoir rock types and properties. So there is, of course, there are disadvantages. We will see what is these afterwards. corrodes injection equipment. A lot of corrosion happening through this using of water flooding. I mean, so what we can do to reduce that corrosion in water injection depends on the type of the material used for our wells, injected wells. What is the type of water we need to use? What is the additives? With the purities of the water, etc. So, what is the treatment treatment facilities? Water treatment facilities we use? It's pure water or there's impurities inside it. So, it's all causes of corrodes injection equipment. Incompatible with reservoir water, of course, there's some incompatibility with reservoir water. Then we have some issue regarding plugging inside our reservoir, how we can mitigate this. It's one of the things happening through the water flooding techniques using to enhance our reservoir pressure and our production. So, water flooding overview, secondary recovery method. It's considered a secondary recovery method. So inject water to displace oil. Why? We know and somehow we have some declining in reservoir pressure. Then we have to inject water to displace oil when we have if the let's say the aquifer not enough to support the displacing of that oil, so we need to use another secondary recovery method, which is water flooding, for instance, in our case today. Maintains reservoir pressure. Again, it's because we losing some power that's pushing the oil to the surface, which is the reservoir pressure, because we have some dissolved gas, and that gas will separate from the oil. Then we have losing the power to produce more oil to the surface. So it's a secondary recovery method. We use water flooding for maintain reservoir pressure. Cost effective is again because it's cost effective. So then it's widely used. So let's see this illustration when we have starting from this point to this point, which is piston and non-piston displacement. We know already what is piston, so it's piston like starting from 0 to 1 when we have all this front going to displace oil from this side from point A to point B. So let me use the pen. So if we decide this is the point A and this is the point B, so all the oil goes in this direction. Let me change the color. So all the water is going from this direction with uniform way. So assume a sharp uniform flood front where water displays oil perfectly. So it's going like this from point A to the point B, like a piston. So pushing oil forward. Is that happening in reality? No. So this is the ideal situation. So we think about the ideal situation, which is we call it piston effect. So what is the non-ideal situation? What is really happening? It's non-piston displacement. So this is the actual what is happening. So the flood front is diffuse with water fingering through the oil. Due why? Because we have viscosity differences. So and there is a capillary pressure forces, or maybe there is of course a variety in permeability. So this all leads to uneven sweep efficiency. What will happen? We have some oil trapped and reducible water. So not most of the oil moves from this part or from this point to this point. And then we have like this phenomenon happens. So it's which is piston and non-piston displacement. So mechanism behind water flooding, it's we need a flood front management because we see from this technique, I mean the water flooding, the water drive can it's most probable and usable technique because it's cost effective and can maintain the pressure. So then we have using against the other type of pressure enhancing in our field. So in this phenomenon, what we can do as optimization strategies. So we use conformance control, which is and under the term of flood front management. So maybe we can use polymer gels to supply the flood front. Maybe we can use capillary trapped oil with chemicals to enhance the capillary pressure here. Example, if we have low salinity for water flooding, and we can monitor, of course, and that's happening, and how we can monitor the water flooding front via reservoir, so we can after injecting here and see what is the results afterwards for the nearby wells for the targeted formation. So of course we have some we have formation target as to inject water inside, and then we can see if that water reached is that the reservoir enhanced, the production afterwards enhanced from the targeted produced well. So monitoring the water flooding front from point A, I mean the injected wells to the targeted produced well, and see we can do that, of course, through our software where we have simulators running to see after a certain period of time what is the effect of this water injection front on the produced well. Okay, so pressure support through water injection. So this is the mechanism behind water flooding. Improve mobility ratio. So what we need to move to I mean to improve the mobility ratio from because it's the simple word of moving from point to point to enhance the mobility ratio for our reservoir. So move oil towards producing wells, enhance sweep efficiency. It's the result for our technique of water flooding. Okay, so recovery efficiency equation, we know this is the equation we use for primary recovery, where we have ER, it's ED multiplied by EA and EV. So what does these terms mean? ER, it's the recovery efficiency from water flooding. ED, which is displacement efficiency, how much displaced through our reservoir, and EA aerial sweep efficiency because we are talking about sorry we are talking about area we have to displace the oil through. So we because of that we need to think about how much we have in terms of area to enhance the sweep efficiency through our reservoir from the injectors to the producers. This is the simple equation for oil recovery efficiency to understand in simple way what is the terms inside and what is the dominant factors to enhance our production. So uh, near injection well, we have a water saturation around 1. So water flood front transition zone. So the SW, I mean the saturation of water, drops sharply as oil is displaced. So we have residual oil saturation remains trapped by capillary pressure. And behind the flood, maybe we have some stabilized saturation. And near producing wells, we approaches reducible water saturation, where only oil flows initially. So, what is the critical concepts for the water flooding? So, it's about capillary trapped residual oil, oil left behind due to capillary forces, and that's will reducing recovery. So this is a key target for enhanced oil recovery method. We can using surfactants to reduce that. And of course, we saw from the previous illustration we have reducible water, and that's more immobile water in the oil zone before flooding. So sweep efficiency can see through the previous. I mean, if we go back for this diagram, this highlights the challenges of incomplete sweep. So we don't have a complete sweep because of that effect. Okay, so let's back again to our equation. So the equation it's parameters. It's the porosity, which is the fraction of rock volume occupied by pores. So higher porosity means more oil storage, and the impact we have the factor of exponent 0.0422. So in the initial water saturation, fraction of pore spaces filled with reducible water before production. And the higher SW means reduces recover oil, so we have that's why we have negative sign. The oil formation volume factor, so it's the ratio of oil volume at reservoir condition to the surface condition. Higher BI, more gas in solution, so this slightly improves recovery. And we have the permeability and thickness for the reservoir. So all these factors to we when we need to calculate the primary recovery, estimating our recovery factors through our efficiency, water drive efficiency. So this equation applies to reservoir where natural aquifer maybe support that displace oil, stronger water influx. That mean we have high KH. That will improve the recovery. And what we can see or we can consider as a limitation for this equation, it's from the API, so it's empirical, so may fit for some reservoir. So why I'm trying to mention this, because when we use the recovery efficiency equation, or I mean the oil water flooding, so we have to consider what we have in terms of reservoir we have. What is the reservoir properties? So is it homogeneous reservoir? So for instance, for this equation, it assumes homogeneous reservoir. So heterogeneity, for example, for instance, fractures can maybe skew some results. So it's typical recovery factor for this around 20 to 40%. So higher if pressure is maintained, of course. And maybe the depletion drive, if we consider there's no aquifer, so maybe it's around 5 to 15%. So we can, from this equation, estimate what is the oil recovery for our field. So how we can maybe consider the optimization strategies for maximizing the oil recovery. So maximize the KH, drill near, for instance, drill near high permeability zone or fractures, where we have more permeable zones than where we have more oil moving from place to place. Then we can extract more easily what is oil near that wells, produce wells. and minimize the water saturation. So use waterability altering agents. For instance, maybe we can that waterability, we know waterability plays a huge impact on which is oil wet or water wet. So maybe we can use the surfactants to minimize that, and control, of course, control pressure. So maintain reservoir pressure through our water flooding. So, what is the main purpose of using water flooding to enhance our reservoir pressure? Then we have to enhance oil recovery efficiency through that. So, what we can consider from this equation, we can see or consider, this equation provide a quick estimate for our oil recovery factors. So, it's a primary recovery for our water drive reservoir, but should be supplemented with dynamic, calculation, dynamic simulation, what we can use in term maybe Ampal or Eclipse for accuracy to understand exactly how we can get more recovery efficiency through our reservoir. Okay, so rock and fluid properties, of course. Recovery efficiency equation, we have to consider some properties for our rock and fluid properties, which is oil viscosity, water viscosity, formation, water composition. So high salinity, for instance, may cause scaling. Of course, if we have more salts inside our formation, may that scaling or incompatibility with injected water. Then we have problem inside our reservoir, and then the sweep efficiency cannot getting the much as we want. Injected water quality, why it's very important, because it's maybe need filtration that we have to think about the water treatment facilities, and what is the chemical treatment to avoid formation damage, scaling, plugging, soaring, etc. For instance, this one of the things happening. I mean the problems when we inject water inside our reservoir and we don't consider what is the water quality used for that reservoir. Is it compatible or not? Is there any related issues with the impurities of that injected water? Then, if not filtered enough and it's not treated enough, then we have some damaging happening to our reservoir. Then we have problems. Gas presence solution. We know, sorry, when we have solution GR, that maybe impacts the relative um, permeability through our uh, water displacement. So high GR reservoir in primary recovery, higher initial recovery because we have gas drive, but rapid decline after gas cap forms. Maybe we have gas cap. So it's a need for pressure maintenance. So gas reinjection or water flooding to avoid that solution GR. So it's provide natural energy, of course, but maybe reduce oil mobility and complicates displacement in secondary or tertiary recovery. So it's need more gas cap management. Okay. So again, to the recovery efficiency equation. So what are the keys to improve recovery efficiency equation? So for the displacement, so lower eliminate capillary force and lower mobility ratio. For the area swept, so lower mobility ratio and maybe modify flood pattern. We will see what is the flood pattern means. Use infill drilling to enhance the area. And lower mobility ratio, of course, modify injection on production profiles. Sometimes we need to change the injection rate or the production rates. Then it's very important to manage the profile of both production and injection to have the right results in terms of mobility and sweep efficiency when we consider our injection rates inside. So use selective injection production program. So how we can manage that or control that using the selective injection of production program. So analyze flow dynamics and modify injection profiles, modify production profiles, all working together to optimize reservoir flow dynamics. Otherwise, we have some problem in terms of recovery efficiency. So it's typical range from 30 to 80%. So do we need 30 or 80? It depends how we can modify production and injection. Sometimes more water injected to the reservoir not mean that we have more oil produced. Maybe we can afterwards when we monitor the injection rates, what is the the mobility ratio needed for our reservoir. So it should be understood through our through our simulation models we used. So it depends on the inputs on inside our simulation. Then we can see what is the production profile. Afterwards, then we have our right production program and injection program. So all these factors together will improve the recovery efficiency. And then we can maybe, of course, for the vertical, reduce gravity segregation, which is play a negative role a positive role in production injection. So waterability, let's take a look at what waterability is. We know there's two type or three type of waterability. It's water wet, oil wet, and mixed wet. So what is the preferred? Of course, in terms of waterability, we know water wet is more preferred through our reservoir because waterability, the more water coating the grains. So oil occupies pore centers. So oil coats grains, water occupies pores corners, and then we can, through dealing with our reservoir, we can pushing more oil easily with when we have water flooding. So it depends on rock properties and what the permeability porosity afterwards. So water flooding works efficiently when we have water displace oil is easily. So it's when we have, water wet. So higher recovery factors, it's around, consider for water wet, around 20 to 60% for water floods. So oil moves, as having said that, more freely and less adhesion to the rocks. But when we have this water wet, what is the type of reservoir it's best for? It's for conventional water flooding because we have low cost secondary recovery. And oil wet rocks, challenging, but can be manageable because oil clings to rock, reducing water flood efficiency. So recovery here, we said here at 20 to 60%, but it's reduced here to it drops rapidly to 10 to 30% without enhanced oil recovery. So what we can use as a solution if we have oil wet, maybe you can add some surfactants to alter the waterability to make it water wet. And low salinity, of course, water flooding promotes water wet behavior. and maybe we can use thermal methods, for instance, steam. So that's reduce the oil adhesion. So when oil wet can be better when we have gas injection. For instance, when we have carbon dioxide, so CO2. So oil wet rocks may allow better gas penetration. So we have less water blocking inside our reservoir. And maybe we have another example of when we have some reservoir, or fractured reservoir, I mean. So spontaneous oil imbibition can occur in oil white fractures, I mean. So what we have as a consideration here, what is the key consideration in terms of potability? So reservoir heterogeneity. So mixed potability is common and complicates recovery. So enhance oil recovery potential. Oil wet reservoir often required thermal or chemical treatments. So again, water wet rocks are preferred for conventional recovery, but oil wet maybe reservoir can be viable with advanced enhanced oil recovery. So it depends on what is the our production phase. Is it primary or secondary phase or tertiary production phase? And what is the economics? Enhanced oil recovery, we have higher cost, but what is the return afterwards? Is it worth to go for it or not? So it's need to understand these factors before we decide what the treatment will be. So different potability mean we have different saturation distribution at pore scale. What is the factors affecting sweep efficiency? So let's see in terms of reservoir. So mobility ratio. We know mobility ratio plays a huge impact on the sweep efficiency. The mobility ratio, it's displacing over lambda displacing over lambda displaced. So it's about permeability and viscosities for water to the oil. If we consider the mobility ratio, it should be less than 1. So how we can manage that? It's more favorable, I mean, to have mobility ratio less than 1. So displacing a fluid, for instance, water is less mobile than oil. So we have maybe stable flood front. So it's high sweep. So low viscous oil with high viscous polymer solution may be more favorable for that. If we have mobility ratio more than 1, so maybe we have viscous fingering and poor sweep efficiency. Reservoir heterogeneity, more sweep efficiency, more oil can be extracted from our reservoir, gravity, segregation, and permeability contracts. And of course, when we think about permeability, so it's play a crucial role in terms of sweep efficiency. So we have higher permeable or less permeable reservoir, then we can see what is the afterwards of the sweep efficiency is. So and for produced water injection, these some challenges and failure modes for produced water variability, scaling, and corrosion. So what is the key performance indicators? How we can see if our if sweep efficiency is working well or not. So we have a matrix for putting as how many I mean the injection rate and the producing rate, the corrosion, is it reduced our injectivity, we have high pressure or not, water leakage downstream, do we have any like these issues? So we should think about our KPI for the water injection, and I mean the sweep efficiency. So water quality requirements, what is the sizes of the particle inside this water injected through our reservoir? Do we need any bacteria to control maybe sulfate, and that's reducing the some issues regarding asphaltene inside our injected wells, what we have seen many times. So we have to think with the water source and treatment. So source, surface, and produce and seawater, all of these, it's a source for the water to use for and produce from the reservoir. So it should be treated and re-injected with our requirement, I mean, water quality requirement for our reservoir. So, what is the, for instance, particle size? Is it less 2 microns? Is less 4 microns? It depends on the studies from the labs, which is compatible water to our reservoir. So all these we have to think about because we need to have a high sweep efficiency. So the factors affecting our sweep efficiency, it's the source of water and treatment for that. So the treatment will consider filtration, deoxygenation, and chemical adjustments. So what we can use to get our particle size and total suspended solids inside our water injected in our reservoir. So removing these solids, it's very important, and maybe we can think about what is the sweep efficiency when we calculate again after treating our water. So ensures compatibility and injectivity. So is that water again compatible with our reservoir properties? Is the injectivity it's compatible with our ability reservoir ability to have high sweep efficiency. So all these factors can play a crucial role in terms of water efficiency, sweep efficiency, I mean. So, sorry, water flood design process, reservoir evaluation. Okay, let's take a look what mean reservoir evaluation. That the data to be studied and collected as reservoir characteristics. Again, we just mentioned what is the rock properties, what is the permeability, porosity, everything regarding the reservoir characteristics, the aerial, vertical extension, isopac, zonation, etc., rock properties, directional permeability, porosity, heterogeneity, reservoir fluid, gravity, formation volume factor, primary production mechanism, what we have in terms of production, what type of production we use, the drive mechanism, is it gas cap, do we have aquifer in our reservoir, what is the pressure distribution inside our reservoir, so oil distribution in the reservoir, is it this place more gas, this place more oil, and this place more oil and water. So we have to think about all this in terms of reservoir evaluation. So then we can think about what is the water flooded design needed for that reservoir. Flood pattern selection. After all these data to be studied, I mean all these things, then we can go for our flooding pattern selection. What is more affordable and compatible according to all these data? So we can run our simulation and think about what is the flooding pattern selection. And after selecting the right pattern for our reservoir, then we can run the simulation and see what is the right estimated after and see what is the efficiency factor for that flooding pattern selection. Recovery projection, what we decide in terms of projection rate, recovery rate, I'm sorry. So is it 10%, 60%, 70%? After all these points done, so then we have to think what is our risk and uncertainty analysis. It's very important. Otherwise, we will see some we will miss. Some risks. So ahead, and then we have to face these risks, but we don't have any mitigation plan because we didn't think about what is the uncertainty in our analysis, and then we don't have any mitigation or plans to overcome these uncertainties. So common water flooding patterns: 5 spot and 9 spot, line drive and peripheral, based on well placement and reservoir geometry. So these the common water flooding patterns. So let's see the layout or flood our flood water flood layout. So a reservoir is necessary for proper choice of what? Pattern selection. So if you don't have your correct reservoir study cycle, so you have to conduct the reservoir study, select your production pattern, and go to adapt what is the real field condition, and you don't have this output as maximized resource recovery. So you need to go through these points. It's very important, it's essential, mandatory, crucial rule to follow before maximize resource recovery. So it's all, and then you have aligned with your objectives of, the goal of reaching 60%, 70% of recovery from your field. Okay, so in-house study, consulting reservoir engineer, the selected pattern should provide the desired oil production capacity. So we have a production capacity. We think about 70%. It's the recovery factor we have. So then it's the oil production capacity. For instance, 1 million barrel per day. Then it should be this pattern. For water flood layout, it should meet the oil production capacity, provide sufficient injection capacity to support the oil. Otherwise, if it's not sufficient, it's okay after selecting the proper, let's say, layout, but without sufficient injection capacity, we don't have the resources enough, then you cannot reach your production capacity. We already said about what is the injection rate, and monitor the injection rate and alter the injection rate regarding what your goals. Maximize oil recovery with minimum of water. How you can manage that? Sometimes you're injecting more water inside your reservoir, but not reaching the maximum oil recovery. Why? Yeah, there's maybe some aspects or risk not you mitigate. For instance, you have fractures or fingering inside your reservoir, and all the injected water goes through the fractures, and you don't have reach from when we said we have point A and point B. From this injection, this producers, you don't have this sweep efficiency correct inside your reservoir, and then you cannot expect what you have to get at the oil production capacity. So maximize oil recovery with minimum of water. So what is inside here? What is inside your reservoir? What is the properties? So it's after conducting reservoir study. Then you have selecting the right proper production pattern. Otherwise, you are missing some points. It's very essential to have and mandatory to have a maximum minimize resource recovery. Okay. Use reservoir heterogeneity to the best advantage and use the existing wells to minimize the number of new wells. What does that mean? The last point, I mean, number five. Sometimes you don't have to drill new wells. Maybe some producers will convert it to injectors, and then you don't have to consider new wells because if we consider this is our reservoir, uh, uh, let's say this is our field, and you have like these producers, and then you want to use the right pattern selection, and then maybe it's good to convert these producers to injectors. So keeping the producers, and it's good to have like these wells as injectors. So this will minimize the number of new wells. So you don't need to have a new wells to be drilled, and then you can use it as water injection. So how you can consider that after studying again, conduct the reservoir study. Otherwise, you don't have, and you cannot imagine what is there any connectivity between these layers, and if this it's effective connection and effective permeability and porosity, etc., like these reservoir properties and characteristics, then you cannot put the right proper selected pattern for your water flood layout. Okay, so this selected pattern is modified as need to fit the condition of the specific field. So this is very important. This pattern can be okay. I select these wells, this the producers and these the injectors. Maybe I can change it afterwards. I mean the producer to injector to enhance the recovery, change this well to injector as needed to fit what I have in terms of oil production capacity. So you have to think about what you can do. It's depend on your monitoring, your outcomes. You have your management of this water flood project. Do you need to select the right proper way? Okay, it should be. So let's have a look of the water flood layout. So this is stacked line drive, inverted nine spot. When you have these producer and these injectors, one-to-one direct line drive. This is the linear. When you have linear injector, linear producer, regular nine spot. When you have these injectors and you have these producers. Another type, regular seven spot. When you have seven producer and the other injector, inverted seven spot. So you can see there's different type of flood layout. It's all depend on your study. What do you need? What is your target? What is the recovery target? What is this preferred or this preferred, and why? Is there any connection? Is there no connection? How you can mitigate the risks you have? Maybe after selecting the right, you think the right pattern, then you can see, and there's a different example. So I mean, let's consider this. So, for instance, if we think about the bubble map, it's this will be going like this, and this will be going like this, and this is still as it is, and this like this. What does that mean? This is the production bubble map. So, what is the effect on this one regarding this one? I will think, okay, there is and not there's comparing in connectivity between and inside the reservoir. So there's a good connection because all the water goes here. We have a good production from this well. But for this one, there's more doubt. So there's more question. Why there's no like this effect in this say this one, and this is number two, and this is number three. So in terms of production rate from well number one, it's not comparable with production. So if we have, for instance, if we have 5 MBD here, uh, MBD, and maybe we have 2 MBD here. So why we have two here and we have five here? So what is the outcome? How we can consider the right area of putting our injectors? Is it inverted seven spot? Is it's fair enough for our reservoir, or, or maybe we can here change this well to the injector and leaving this injector, and we inject through this one because there's afterwards, after studying the reservoir layers, there's a good connection between them. Then we can enhance the production from 2 to 5 here and get what we've planned as I mean the targeted oil production rate. So these questions can be raised and ask yourself through your simulation, is that what we need from this water flood layout? Okay, let's continue. So this is the for spot, skewed for spot. You can see there's different type of pattern boundary depend on what you need in terms of target. So, for instance, this called pressure maintenance when water inject supplements declining reservoir energy from solution gas. So this is what's called peripheral flood when we have like this type of injectors surrounding the producer. So it's we have when we need a maximum oil recovery with a minimum of produced water. Because the number of injectors is smaller than the number of producer. When we have when we consider like for instance if we have a less budget for our injector, and this can be fit to push all the oil in this area towards the producers, then we can use this preferable flood as a selected pattern for our reservoir to enhance the production and enhance the reservoir pressure. Regular nine spot. Um, Again, it's one of the it's depend on the position of producer, and here you can select the right pattern. So you can see there's different types, and these types even it's not like what we've seen just in seconds. It's said suggest nine spot, but you can see it's the location of the producer. It's not similar to what we've seen. It said suggest nine spot, but it's depend on what we need and what type of we call it now nine spot. It depends on our targeting of our production rate. Okay. So pilot test. Why do we need pilot test? What is this related to flooding patterns? So any prediction of reservoir behavior under water flood has a high level of uncertainty. So why we have uncertainty? Because we've just seen the maybe from example some wells doesn't produce as much we planned through our flood pattern. So why pilot water flood project is small scale project carefully selected. Let's go back. So let's say this is change the pen. So let's see, we select this area to go for a pilot project. We will not do all the project. I mean, not injecting all in all these. We will select this area. This is a small area as a pilot project. Then we can see is that it will help verify the response calculation and possible problems. So it's not only the response calculation. I mean, what's this response calculation? It's mean the injectivity, mobility ratio, production from produced oil from these producers, and possible problems. Is there any problem regarding the connectivity inside the reservoir? Is there any problem regarding there is a plugging, any type of water compatibility with the reservoir fluids, etc. So all these things can be considered and monitored carefully because it's to have the right response calculation, and then to consider what is going on inside our reservoir. Then we have considered possible problems, and then we have the right solutions. So it can cause a delay in the implementation of a full field water flood. Okay, so this is the why we have it. So this is the we call it here pilot. So this is the pilot project, and sorry for my writing. So, and this is the normal project. So maybe because we do all the calculation here and see the response is not as much as we want, so we will not go to the second phase. So this is the phase one, and this is phase two, and we will not moving forward to the normal project. Why? Because we've seen there's a problem in terms of the outcomes of our calculation. So this will delay implementation. It can also save the cost of potentially unsuccessful full-scale project. So that's why some companies goes for pilot test. We have it, we've seen it. There's a and conducted in our reservoir. We have pilot test, and then we can see. It depends on the time considered for the project. Is it inside it, or I mean, is it 1, 2, 3, 4 years project? So from day one, we have a pilot test for 3 months, 6 months. It depends on the outcomes and what is the response calculation. So injection wells and spacing. Well spacing is determined by the primary drilling spacing. Producer are converted to injectors, maybe. New infill injection wells are drilled as required when we have, for instance, we need to drill new wells. Production loss from converted wells. So we have to consider how much we lose because we convert some wells to inject wells. So what is the production loss? It should be considered because we have a target oil production rate afterwards. Usually very low net oil rates when water flood is applied. This is what are usually consider seen because when you have convert some I mean produce well to inject wells. So loss in only temporary loss of current production. So it's considered as temporary. So it's not a long-term loss because when you have a conversion from type to type, then you are considered through your your calculation. I mean the recovery factor that will enhance the recovery factor, and if it's enhanced, so it's a temporary loss. So you maybe lose 2, 3, 4 MBD from those wells, and in overall maybe 10 to 50 MBD. Then we can use after converting this is a successful project, then you can have 10 I mean 100 or more than 100, for instance, from this project of converting producer to injector. So our production rate will be enhanced by successful water flood. So after selecting the right flooding pattern and converting some wells if we need it, then you have the successful water flood. Water injection is usually started early in the primary producing life of reservoir. Usually. So why it's usually? Because you don't need um, going back again. This is the production profile. So starting from this and you reach this point, what we call it plateau rate. So it's a plateau rate when you have a stable production in this period. And you don't want to reach this point. Why? Because at this point, the production will decline. So for instance, when you start production, maybe you can start here or here or here. So it's from the early point you have a water injection profile, and this will extend the plateau rate. You don't want to be in this period because when you have declining in production. So you're losing return of a value from produced oil. Then you have to consider the water production injection, and maybe this can be. I mean, for instance, if we consider the time, it will be a long time. So if you have early started primary producing life in your reservoir, then the plateau rate will extend and you have afterwards then maybe declining, and so you consider another type of enhancing your reservoir in your term of recovery factor. So, okay. So water injection is usually then because of that started early in the primary. Terrain and topography. Sometimes the pattern it's depend on your well location and spacing and the equipment needed for like these conditions. So this will affect well pattern. So if we go back a little bit, see, so sorry. So you can see from here, it's not regular one because the well location it's different from well to well. It's maybe this because of the topography of the field. Then you cannot consider it's in one line all the wells. So because of that, you have considered the other well spacing for your well injectors. Okay. Marshes, for instance, if we take like this example, marshes, lakes, rivers, urban areas, mountains, etc. All of these consider terrain and topography when you have affecting the well pattern. Okay. Selection of flooding plans, it depends on the spaces. Because of the spaces, it's play a crucial role in using the right flooding plans. So you have to consider what the spacing, and then you can consider the effect of injectors on your producers. So then you have to select the right pattern for your field. Innovative water flooding techniques. What do we mean by that? Uh, maybe you can use horizontal wells. So for horizontal wells, you have if we consider the horizontal wells, if we consider this is the vertical, and you have this layer. So it's only this area. So when you consider the horizontal wells, so this area is connected to your reservoir, and then you have much area can be affected by injection, when water injection, I mean. And then if you have nearby horizontal producer or vertical producer. So it's more affecting, more enhancing the oil recovery from these wells. So one of the techniques you can use, it's converting or drilling or maybe multilateral wells when you have horizontal well, because you have a huge drainage area. Then that drainage can affect the production profile for your field. So smart water. I mean, when you have adjusted salinity and pH, polymer assisted flooding, horizontal injectors, selective zone injection. So what does that mean? Uh, so when you have injectors here and you have a producer here, so maybe this well is perforated in this area. So let's change the color to make sure it's me understand. So this formation one and this formation two. So selective zone injection, maybe you want to inject only in this area and enhance production from this interval, and leave this area not, there's no injection because maybe there's a aquifer support or gas support. So the pressure here, there's no problem with it. Maybe you have more water produced, so high water cut. So you don't want to increase that water cut from this interval. So only injecting in this interval and enhancing the sweep efficiency for this area. So selective zonal isolation injection. It's very important to have right proper injection model for your reservoir. So you have to think about, is it one area or two areas when you have to consider for your injection profile. Okay. So fractional flow analysis, calculation fluid saturation, how your calculation goes in terms of your fluid saturations, helps determine breakthrough timing. So having said that, when we have um, this producer, when you this is the formation and is perforated here. So where the breakthrough of water or for instance breakthrough for fingering, for you have fingering effect inside your reservoir. So you left some part of portion of oil. It's not recovered through your production injection profile. So that's mean let's change the color. That will be good. So this oil, it's remained unrecoverable through your production profile. So you have to think when this phenomenon can be happened, and then you can eliminate that factor by using another type of production profile, injection profile. Guides optimization of water injections. This will, of course, guides you through the most probable effective optimization model for your injection. Okay, so continue on innovative water flooding techniques. Maybe you can use polymer assisted flooding. So the most common used polymer in oil field flooding is what we call it HPAM. It's partially hydrolyzed polychloroamide. So most of the companies using this type of polymer because we have it in high molecular weight. One of the factors is water soluble, cost effective, and improve water viscosity. So the HPAM, it's low cost, high viscosity at low concentrations. with shear thinning. What is the limitation of that type of polymer? It's degrades at high salinity and temperature. So you have to think about the temperature of your reservoir. What is the salinity of your reservoir? Maybe we have you can consider the another limitation. It's mechanical and chemical degradation. It's best for a reservoir with temperature around 75 centigrade with low salinity, around less than 20,000 ppm. So you can choose the best polymer to assist your profile of, I mean, water flooding profile. You can change to another type, for instance, xanthan gum, which is a salt tolerant stable at high share, but it's more expensive. So why we go first for this type? Because it's cost effective and cheap, comparing with xanthan gum, uh, which is used, the other one, I mean, the xanthan gum used with high salinity reservoir. So there is different type of polymers. We can select which is best for our reservoir. What is again and again and again, without using proper studies for your reservoir, you cannot do the right proper way of implementing your water flooding, because the study will gives you the right keys to use for your implementation of your flooding techniques. Okay, so other advanced types include, as we said, xanthan gum. It's tolerant to salinity and temperature. It's used for high salinity reservoir, more than 75 centigrade, and yeah, more than 20,000 ppm. Hydrophobical modified polymer HPMs, so it's advanced for high temperature or high salinity reservoir. So again, there is different type, modified type for polymers. It depends on your use. So when you want to use these types in your field. So the HPM dominates over 90% of the polymer flooding market. Oh, so that's why it's more selected by the companies. Why? Because it's cost effective. Effective at low concentrations, 200 to 2000 ppm, compatible with reservoir brine with proper treatment. So that's why they use partially hydrolyzed polycrylamic HPAM for in water flooding. Okay, so this is the how the HPM works when it's injected inside the reservoir, and uh, 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 the effect afterwards using the uh, uh, using this polymer with the water flooding uh, profile. So the simulated results show that all simulation have a stable layer. So it's more stable layer order on a clear crude oil. Uh, and oil water interface after dynamic relaxation equivalent. After when you have it, it's more relaxed and equivalent with the reservoir, so you have more clear crude oil water interface. So HPA molecules were agglomerated in different forms as the crude oil water interface betting on in organic cations in the water. So that's why, because they studied what this polymer can interact with the reservoir rocks and properties. Then it's they seen there's a proper results when using like this type of polymer, and having said that, it's more cost effective and it's more compatible with water reservoir. So the stability of interfacial film was positively correlated with a gyration radius of HPA model. This study was implemented and see is it more suitable to use this type of polymer. So, polymer flooding is chemical method that widely used in enhanced oil recovery (EOR). So it involves changing the rheological properties. That's why we need like these type of polymers to assist with changing the rheological properties of the fluid inside, displacing fluid inside our reservoir. Then we have enhancing our sweep efficiency. So after using these polymers, more sweep efficiency we've seen, and then we can, because it's more soluble with the reservoir water, then we have a good results in sweep efficiency and our targeting oil production. So it's more commonly used for with water flooding profile. Of course, horizontal injectors, having said that, because it's more having area that's connected to the reservoir, and then we can see there's more affecting of injecting water can be reached to the area of producers, and then if we have considered our horizontal producer, we can reaching more area with less cost of uh, injecting water inside our reservoir. Then the sweep efficiency will be enhanced after using this technique for our injection profile. So more gas or water injected, more gas or oil produced. So what do they provide to reservoir? Enhanced contact area. That's what we want from our horizontal wells. So more contacting area, then we can reaching enhancing, I mean, the sweep efficiency of our reservoir rather than just using the regular typical type of vertical wells. So reduce coning and channeling. That's because horizontal wells with more connected area to the comparing to the vertical, then we have a good contact with the produced oil wells or gas wells. Then we have a less of coning and channeling if happening through this type of injection wells. By distributing injection pressure across a long horizontal section. Of course, one of the primary objective of using water flooding is to enhance reservoir pressure. So when you use the horizontal wells, we have a long area of enhancing the sweep efficiency, enhancing the production, and enhancing the pressure that enhancing the production rate from our producer. So this will minimize the local high pressure zones and can be because water or gas coning and channeling, improving displacement, and we have good management of waterfront management through our horizontal wells. Uh, well, that's mean more stable condition of production. So it's improve pressure support, selective zone control because we select the zone. Maybe we can select the area we can close through what is called clever selection or I forget the term. Not clever. Oh, sorry for that. When we have to select which zone we can inject through shutting or opening some perforation for injection and close the others when we've seen, for instance, increasing in water production in some areas. So selective the right zone to inject more easily through the horizontal wells because it's the connected area, it's long enough rather than the typical one of regular vertical wells. So because we have horizontal wells, we have high permeability streaks, and then this high permeability can enhance our production profile. I mean, injection profile and production profile. So it will delay water breakthrough. Because we have selecting the right zones, it will delay when we have when we conducting any surveillance for our reservoir to see when we have possible water breakthrough, and we can select the right production profile because we have select the right injection profile. Then we can, after monitoring our production and injection profile, we can select the zonal isolation, proper zonal isolation for our injection profile. Then we can reduce or delay the water breakthrough. So the careful placement, horizontal injection, push oil more uniformly towards our producers. That's why we selecting horizontal wells rather than using vertical wells in our production injection profile. Okay. So, taking one of the examples, the field example, Marmol Field in Oman, PDO, Petroleum Development Oman, PDO is shortcut for Petroleum Development Oman. When they have flood and his polymer to enhance the production in I mean in water flooding. So it's located in South Carbonate Reservoir. The thickness it's 10 to 20 meter. It's a thin layered reservoir. All viscosity between 10 to 15 centipoise. So it's considered a medium viscosity. Initial recovery natural depletion followed by water flood. So this is the initial recovery mechanism. So having said that, we have to consider what type of production profile we need to use, and what is the target, and then what is the challenge, because it's thin, heterogeneous carbonate layers with strong permeability, poor aerial and vertical sweep efficiency. They have early water breakthrough, and the sweep zones where significant bypass oil remained. So these the values pre-polymer and post-polymer. So you can see there's a significant improve in mobility ratio after using this polymer. So this is the outcome of using the polymer in their flood profile, water flood profile. Okay. Again, what is the selective zone as an injection? When we select the right zone to inject water to reduce the water breakthrough, and we have only oil. So, for instance, for this interval, we can close it and inject. In the other intervals, we have more oil than water, so we have less water produced through our injector profile. So longer horizontal section increase contact area but require more complete completion and injection control. So that's why we need to select the right zones for all our injectors. So, for instance, slotted linear or screens for uniform injection, multi-zone packers. If we have some packers, we can open and close others. for the selection of which preferred zones to inject through to reduce the water production and keep only the oils. So perforation strategies depend on the perforation strategy because after conducting the log and surveillance to see what is where the oil column is, then we can select the right proper interval for our perforation strategy. Okay. Challenges in flooding. Sorry, I maybe it will be a little bit longer. I hope you can. I still enjoy it. So corrosion and scaling, injectivity decline, and water breakthrough, zonalization and conformance. All these are challenges in our water flooding. So corrosion and scaling. Why it's considered one of the major factors and problems inside in our water flooding because always we have corrosion because incompatible water or and unwanted material selecting for our injection profile, then and compatibility of produce injected water with formation water, then maybe we have like these problems and damaging the wellbore tubing and the pipelines in the surface. And these can consider the major players of increasing the budget for maintenance and removing like these scale or replacing these type of tubings because we have asphaltene or and this corrosion maybe leads to holes inside our tubing or casing, and then we have losing some injectivity from our profile and water injection profile, and then we lose some oil produced afterwards. So it's one of the major players in terms of the factors affecting our water injection. So uh, this type of pitting our corrosion, what pitting corrosion, when you have it inside your uh, 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 completion and for the injection. For instance, when we considered converting some producers to injectors, so it's still the same material, but the type of fluid used, it's different. So these may be one of the causes of corrosion inside water injection because you don't have the right material. Then okay, for some period of time there is a good profile of injection, then we have corrosion afterwards and one these of the type of the corrosion. So you have to consider the mitigation for this. For instance, vacuum towers for deoxygenation units, chemical scavengers, or corrosion inhibitors to reduce the effect of corrosion and scaling in your material and your injection wells. So all this depends on maybe material selection. Having said that, you maybe you convert some producer to injectors, so still the same materials for producer, but for injectors not compatible and not useful. So it's you have to think about these factors when you convert some wells from producer to injector. So it's depend on the material selection. So mitigation size for scale, water compatibility testing, because you don't need to see like this. So as you can see, this is in the facilities inside your injectors. So all this will reduce, of course, the amount of water reaching to your reservoir and amount reaching through your reservoir to the producer. And of course that will enhance not enhancing the sweep efficiency. So you can say use, for instance, scale inhibitors or pH control to reduce carbon scaling, regular pigging or acid washing, for of course to remove all these scaling from your wells or and facilities. Of course you have to consider the timing of removing like these scales and losing production because of the maintenance project. So softening of filtration units, all these type of mitigation strategy for scale and for mitigation for strategy for corrosion. Okay, so what the type of innovative techniques you need to consider in terms of sorry uh, monitoring your injection wells. So it's fiber optic sensors. So the fiber optic sensor, for instance, in corrosion solution, so you can monitor the corrosion rate. So in terms of corrosion rate, so these sensors can tell you exactly if there are any problem in any point, and you have to take the right mitigation process started right away to reduce the corrosive inside your pipelines, inside your wells, inside your facilities, and then you can extend your life or your facilities on pipelines. So these techniques, it's very now common because it's more useful, more powerful, handy tools. I mean, the fiber optic sensors to monitor what's going on inside your pipelines and wells. And then you can reduce the timing of maintenance and losing production from these even injectors or producers to reduce these kind of corrosion stress and effects inside your wells. So putting the right sensors for used injectors can reduce the effect of corrosion levels inside your materials. And injectivity decline, of course, you have to think about when you have a filter cake or outside your reservoir. So formation plugging, one of the type of problems happened when you have afterwards using the injection profile. So type of cake happened in maybe in external or internal inside your reservoir, and then you have some mechanical issues you need to use to remove these type of formation plugging and formation damming because of this contamination of clay inside your reservoir, and that not enhancing your injection profile. So what type of mitigation or removing tools to use is depend on the what's happening inside your reservoir and what the problem is. So what is the innovative solution applied? Smart water injection. What does that mean? Alters waterability, reduce near wellbore resistance. Companies like, for instance, Ecuador in North Sea and Saudi Arabia using like these techniques for smart water injection to enhance the water injection profile and reduce like these effects by altering waterability. Pulse injection and pressure cycling. So, for instance, you can change the injection profile and change the amount of water injected through your reservoir. Maybe can enhance like these or reduce, I mean, these plugging in your formation shall BP like using like these tests in tight sandstone, for instance, and that's one of the a good example when they reduce the plugging in their formation. Microbial enhanced water injection, which is stand for MEWI. So it is beneficial microbes to clean near wellbore. So they use like type of bacteria to reduce the effect of like these cakes inside the reservoir, and then reduce the effect of this filter cake, and which is affecting the injection profile. Advanced well completion, of course, advanced well completions by selecting the right zonal isolation and injection profile. And the last one, it's nanotechnology application. It's based on to modify rock compatibility again, or to unblock pore throats inside the reservoir. So these technologies can enhance or reduce the filter cake effects. These effects can reduce the block for your formation and the formation damaging. Okay, so another example for ejectivity decline, a decline after fill-up. So the fill-up point is reached. I don't know why it's not. Uh, I don't know. It should be illustration here. It's not. We cannot see. You cannot see how this example, so we will pass through. But it's it's for injection when you have reaching the point where you fill the pores inside your reservoir, and then the production the injection decline, because there is a pressure interface between injectors starts. So it's between in the injectors themselves. Water injection into one well causes pressure buildup felt by surrounding wells. So it's uh, uh, like this profile. So in this point, you have these problems occurs. So the limits additional injection rates per well. So you cannot inject more oil. For instance, you have this injector. So the formation cannot take, for instance, if you inject 5 MBD per day, so you cannot inject 6 MBD because it's reached full capacity of injection. So you need to think about how you can enhance the injection rate through your formation. A horizontal portion of the curve, you cannot see it's this one. Injection rate flattens or even drops further. So here there's extra drop in the injection rate. So we have to think when this can be happened, because this will limit the injection rate. The relevant mitigation for that, it's zonal isolation or use horizontal injectors, because use horizontal injectors, it's depend on because it's a large area, so you can select more area to inject through it. So it's more reaching the number you want to use for injection rate. So optimize injection scheduling. That mean maybe you can inject 5 here for 1 hour, here for 2 hours, here for one day, so etc. So it depends on what's the outcome of pressure buildup for the nearby producers. Okay. Monitor pressure transit data to detect early interface. Uh, because you have uh, pressure injection profile, then you have production profile, so you can see what is the pressure inside your formation. So when you monitor this profile of pressure transit data, so it will detect early this phenomenon. It could be happened when I mean the interface. So all these can happen through the injection profile. Uh, let's take another example for Oxy company, which is it's an American company, very famous company. They their mission, it's our their vision, it's to have like a sponge. So they think about the major oil aren't running out of oil. So this is like a mission or a vision for their work. So unlocked 45% more oil with 30% lower completion cost. By what? What they already had. So this is the key point. So they have this reservoir, and this is they already had. So more 45% of oil with 30% lower completion cost. So this is they have as a successful example of increasing in cumulative oil production and reducing in completion cost. So a six optimized valve versus nine, improve sweep efficiency and better reservoir conformance. So this is what they achieved, a higher water injection rate only where it created incremental values. So they use what's the best injection rate, but after seeing what is the advanced modeling they used to optimize their injection rate. So this is the achievement for their 45 increasing in cumulative oil production. So it's a very huge increase of as a target for their work. So this case is proof that field wild returns can be unlocked through smarter wells. So this is the key point here. So this is the innovation in their work. Smarter wells, design and simulation. So it's they design their wells and run the simulation and see where they can get the highest producers and the good injectors, not just capital spend. They just not want to spend money for nothing, but they want to spend money for something rewardable. So it's worth to go for. So it's one of the good challenges and successful projects by Oxy. So operators where can apply. Uh, okay. What can AI bring to water injection? So AI transforming water injection for efficiency and sustainability. So high cost and unsustainable practices plug water injection. After implementing AI, so they do the optimization and it can be optimize the operation, enhance efficiency and improve decisions. What we can achieve better resource management and sustainable practices. So pattern optimization and dynamic injection adjustment through using the right proper AI tools, analyze because they do, and through them we can analyze historical injection and production data. So this is the first point. Analyze historical injection rate and production data. Recommend which injectors to ramp up or down. Again, if we think about this is the injectors, how we can inject water through, and then we can have how much oil from this layer through the producer. So recommend which injectors to ramp up or down. It's mean how much barrels can be injected, the amount of water, balance reservoir pressure without over injecting. This is most powerful statement I will say regarding using the AI, because then the right analysis, historical analysis, it will give the right decision making afterwards. So without over injecting. So we don't need to inject more water inside our reservoir. Then we can have the right production rate for our oil producers. So who's doing it? This is one of the question you can ask. Who's doing this project? Anchor, it's in Norway, uses AI to manage smart water injection. Sorry, let's raise that. So this is one of the companies using this tool, AI tools, in North Sea. If you know, Norway is located in the north of Europe, and on the North Sea, adjusting salinity and injection patterns in real time. So this is the point. It's wonderful one. I think it's injection patterns in real time, salinity injection patterns in real time. So they have all the data in real time. So they adjusting. Uh, this is the key point here. So having said that, we agreed we can do some alteration or in our injection profile. So this is the key point, adjusting salinity and injection rate in real time. So this is the point here when you have these successful projects using the AI tool and using it in the right manner. Uh, okay. So what is the results? We need to know what is the results. 5 to 10% increase recovery and reduce water handling costs. So this is a major achievement for the Incor company to have 5 to 10% increased recovery. Aramco has achieved improved conformance control and delayed water. Aramco, it's an American company controlling and managing the Saudi Arabia oil fields. So achieved improved conformance control and delayed water breakthrough in pilot project, but it's in pilot projects. So, what is our conclusion and takeaways in our water flooding boosts our recovery, of course. Proper design ensures success. Innovation enables efficient operations. So, innovation, of course, enables efficient. Monitor, adapt, and optimize continuously. Always, you have to monitor, and then you can adapt the change and have the right optimization after the right decision to continuous production. Thank you very much for your attending today. I hope it not take a longer time, but you have the right and expected outcomes from this lecture today. Thank you very much. So, if you have any question.
Thank you, Mr. Mohammed, for your informative presentation on innovative water flooding strategies for maximizing oil recovery. Please let's review the questions and answer them.
Okay. Yeah. So we already explained that potability and relative probability on water flooding because they have a crucial role on changing the is it water phase or uh, oil phase in term of sweep efficiency. So more we said it depends on the reservoir properties. So you can see what is your reservoir properties because it's if the I mean the waterability is it water wet or oil wet. It depends on reservoir properties. Again, using the right sweep efficiency, if it's water wet or oil wet, if it's more gas reservoir or the normal reservoir, I mean more heterogeneous reservoir to use which type of and I mean to reduce the effect of if it's oil wet or water wet. So it depends on reservoir properties. Then you can decide how to mitigate these factors. Uh, Another question. What challenges are associated with innovative water flooding techniques? There's different type of challenges. Good question, actually, because for instance, if we take using sensors, so it's real time. So if you don't have the right sensors and you cannot detect for instance, the corrosion rate inside your pipelines, or you don't have the right sensors and the right injectors, then you cannot say you're receiving the right data in the right time, in real time. Then you cannot have afterwards the right decision to alter your projection, I mean, the injection rate through your day, or the targeted injection rate in your reservoir. Um, Thanks a lot. What future trends are expected in water flooding for oil recovery beside AI? Um, for water flooding, it will still using it's. Thank you for your question. For future trends, having like these examples beside AI. So it depends on again on your reservoir, because AI now more widely used to enhance the decision making. So if you think beside the AI, you have to think about what is the type of your reservoir, what is the target of your production rate, and then you can decide what is the is it you need do you need which type of polymer to inject your reservoir? Is it do you need to inject foam, for instance, with your polymer, and do you need to inject what type of polymer to inject beside your water flooding profile in your reservoir. So all these type of thinking of what is the reservoir properties and rock properties and characteristics to understand well before going to using the right flooding, water flooding for your oil recovery. So how you can control and balance between water injection and producing? Thank you for your question. uh, Balancing between water injection and producing, we already explained this question. So repeating the answer is through monitoring. So if you want to inject, and for instance, 100,000 barrel of water, and you want to produce 1.2, I mean, in terms of mobility ratio, more mobile factor for your producer. How you can manage this amount of production regarding what this amount of injected water in your reservoir. So is it the daily basis? Is it for a month or 2 months? It depends on your monitoring and your target. So if that target cannot met, so there is a problem in your I mean water injection profile. So do you have to, for instance, if we consider the example previously, balancing between what injected inside the reservoir, and is that enhance the reservoir pressure, and that enhance the target production from your producers. If not met, so there is a certain point you have to think about in terms of compatible water, or there's plugging, or relative permeability modifiers, etc. So there's different factors actually to think about balancing between water injection and producing. How I can control corrosion? We already explained this question. So controlling corrosion through adding more additives to your injectors. So these factors can reduce the corrosion rate inside your injectors. And currently using the AI technology and monitoring through sensors can control the corrosion rate, because you can see in real time what is the corrosion rate for your materials. I mean materials inside your wells, or the surface facilities, and then you can decide do you need to inject any additives to enhance or reduce the corrosion rate, or keep it as it is. So it depends on installing new sensor to have the real-time data and the maintenance plan for your facilities. I don't know if this is the last one or not. Yeah, I think this is the last one, doctor.
Okay, Mr. Mohammed, please can you show us the image which didn't appear on your slide? I think I sent it to you. If you
Uh,
can check your inbox,
just a bit.
if there a possibility.
Um, uh, yes, I think you can see the screen right now.
Yes.
Just a minute. Yes, so this is the screen for example of. Let me erase. So the eraser not working. Sorry. So from this illustration, you can see where's the interface happened between the injectors, and there's a failure and fill up of the pores, and there's a reduce in the injection rate because there's an interface between the injectors and themselves, and there's interface between the filling of fill up of the pore spaces inside the reservoir. So you have water injection in term of barrels and injection rate. So it's dropped significantly because of that factor. The interface and fill up. So this is the one of the example of injectivity decline.
Okay,
Uh,
Mr. Mohammed.
okay.
Okay, that's good. As we conclude today's webinar on innovative water flooding strategies for maximizing oil recovery, we would like to extend our sincere thanks for your participation. It was a pleasure having you with us, and we look forward to welcoming you to future events hosted by Enkido Training. A special thank you to Mr. Mohammed Al-Jawhar for his valuable presentation. Your contribution is greatly appreciated by Enkido Training Team. Wishing you a pleasant day ahead. Goodbye, and thank you once again for joining us. Bye bye.
Thank you, Doctor, and thanks for Enkidu Training for this opportunity, and thanks for all the attendees for attending this webinar. Hope to see you again in the next webinar and courses through Enkidu Training Center. So thank you again.
Bye bye.
Bye.